We are mapping the quantum spectrum directly to arithmetic Galois representations. The goal is to show that the Langlands correspondence arises from the stability requirements of a unified field theory. The architecture follows a rigid flow. Spectral projection theory filters the quantum states. J-theory applies stability criteria to those states within the moduli space. Finally, Logos field theory generates the field equations that govern the entire system. This framework requires a dictionary translating continuous complex geometry on the left into discrete arithmetic settings on the right. The core maps the geometric J functional to the logarithmic L function action, establishing the critical J equation as the equivalent Hecke eigenvalue equation. Mastering these precise mathematical identities is the prerequisite for deriving the field equations that integrate the continuous and discrete places of the Adel ring. We force chaotic microscopic degrees of freedom, the Dirac traces, into a deterministic limit using GUE filtering, restricting them to a random matrix ensemble. The logarithmic repulsion between eigenvalues acts as localized pressure, functioning as a spatial stabilizer against geometric coupling. Macroscopically, this smooth distribution of eigenvalues translates directly into the spatial volume element of the critical J equation. By setting the terms to zero, we derive the macroscopic equation of state, a mathematical requirement for the field's variational stability. This global action is the theory's engine, integrating the Logos field over the entire Adel ring. The sum includes continuous Kähler-driven actions at Archimedean places, discrete Brouhat-Titz actions at finite places, and a global relational core enforcing strict reciprocity. Applying the variational principle splits the unified system into two local field equations. At Archimedean infinity, a nonlinear J-Laplacian couples the field to continuous background Kähler forms. At finite primes within the discrete Brouhat-Titz building, the field responds to Hecke difference averaging operators. Bridging this gap, solving continuous metrics and discrete arithmetic trees simultaneously, is the synthesis's central difficulty. To understand local propagation, pause the video and try to solve for the Green's function of a point source on a radially symmetric Q+1 regular Brouhat-Titz tree. This explicit solution uses a characteristic quadratic equation to isolate the stable root, defining the field's decay as it moves away from the source. The denominator is the spectral filter, the inverse local Euler factor, locking the field's decay rate to the prime's arithmetic properties. This discrete kernel weaves isolated arithmetic point sources into our macroscopic continuous metric landscape. These local solutions are bound together by the Adelic interlocking condition. This global state is scaled by the Dedekind zeta function, ensuring the field is consistent across the entire Adel ring. To find the physical manifestation of this field, we take the functional derivative of the action with respect to the Archimedean metric structure. This variation produces a classical stress-energy tensor. The left side of the tensor maps the continuous spatial curvature, the direct response to the energy distribution of the Archimedean wave functions. The right side represents arithmetic pressure. The localized Hecke eigenvalues actively carve conical deficit angles into the spacetime geometry. This identity shows that the Gillet-Sol Archimedean metric is the macroscopic manifestation of the Logos field's stress energy. The curvature of the universe is the result of the field's energy density decohering into classical geometry. We have established three pillars. First, J-theory provides the critical equation that stabilizes the continuous geometry. Second, the Adelic bridge formula merges that geometric energy with discrete arithmetic Euler products. Finally, Logos field theory drives these interactions to decompress into the stress-energy tensor of classical reality. The Langlands correspondence is the functional constraint that locks arithmetic data to the curvature of the physical universe.